Imagine walking into a dark, incredibly warm room. In front of you stands a machine larger than your bedroom, but there's no screen to look at, no keyboard to type on, no mouse, just thousands of thick cables and humming vacuum tubes. If you wanted to tell this machine what to do, you couldn't open an app or run a script. Early computers didn't understand code. They only understood raw electricity, the physical presence of an on voltage or an off zero. Because of that, changing a simple mathematical task meant you had to physically rewire the machine by hand. You spent hours, sometimes days, plugging and unplugging hundreds of heavy cables across massive switchboards. The word software didn't exist yet. Operating these machines was an exercise in pure engineering survival. But long before anyone ever plugged in a single cable, the core concept of programming had already been entirely figured out. Over a century earlier, a mathematician named Ada Lovelace looked at the design for a mechanical, gear-driven calculator and realized these machines could follow abstract logic, performing specific step-by-step instructions rather than simply calculating sums. The very first algorithm was written through human imagination. The problem was figuring out how to force physical hardware to actually execute that abstract logic. By World War II, that challenge became a matter of life and death. The military needed complex ballistics calculations instantly, and manually swapping cables on a giant switchboard was far too slow. To speed things up, engineers created a system where physical cable connections were represented by numbers. Instead of patching a wire to tell the machine to add two values, you could feed it a two-digit code, like 01. This was machine language. But this required managing thousands of arbitrary numeric codes. You had to memorize grids of raw digits to outline complex logic, and if you made one single mistake, a 0 instead of a 1, the entire calculation failed. You no longer had to pull heavy wires, but you were still forced to think exactly like a machine. Pioneers like Alan Turing started asking a different question. Why should humans have to speak the machine's language? Why couldn't we build a system that understands ours? This transition led to assembly language. Now, instead of memorizing a grid of numbers, you could type short, logical text commands, like add or subtract. It was a massive improvement, but it was incredibly dense. It looked less like human language and more like a cryptographer's shorthand, readable only by highly trained specialists. It was the first time the rigid architecture of computing bent toward human communication, but it was an incomplete bridge. And you still couldn't type those text commands on a screen. You had to translate every line of logic into a pattern of holes punched into thin, fragile paper cards. A simple program might require a stack of 300 cards. You would spend hours meticulously punching them. Then you'd carry that stack across the room. If you tripped and dropped them out of order, your entire program was destroyed. Executing code required the precision of a mathematician and the patience of a saint. In the 1950s, a team developed Fortran, a high-level language that allowed programmers to write using actual mathematical formulas and sentence-like structures. This was possible because of a new piece of software acting as an automatic universal translator, the compiler. This diagram shows exactly how that translation works. The compiler takes your mathematical logic and cascades it down, first into assembly commands, then into numeric machine code, and finally into the raw electrical pulses the physical hardware requires. Humans could finally speak in their native conceptual tongue, leaving the machine to handle the heavy lifting of translating it into electricity. This creates a circular problem. If a compiler is needed to understand a high-level language, how do you program the very first compiler? They had to build it step by step from the absolute bottom. Engineers wrote raw binary logic to create machine code. They used that machine code to build assembly language, and then they used assembly language to write the first compiler. They were constructing a massive staircase while balancing entirely on the very first step. Every piece of software you use today, your apps, your operating system, the language you might be learning, rests squarely on top of this invisible original tower. Right now, you can open a laptop, type a command on a screen, and run a script in seconds without ever thinking about raw voltage. The engineers working in those massive, screenless rooms were inventing the conceptual framework of coding itself. Our entire modern digital world exists because those pioneers survived the era of hardware and taught machines how to listen. If you were thrown back into that era, do you think you'd have the patience to survive punch card programming? Let me know down in the comments. And if this look into computing history was helpful,